Now, one of the most important things about any star is its temperature. And we're talking about stars that are light years away. How the heck do you take the temperature of something that is very, very, very far away? Well, of course, this is going to involve light. So let's back up just a little bit. All matter vibrates. You, me, the cup of coffee sitting on your desk right now, every single molecule vibrates. And when things are cold, they vibrate just a little tiny bit back and forth and back and forth. As things get hot and more high energy, they vibrate faster back and forth and back and forth and back and forth. Their vibrations are more violent at high temperatures, and they are less violent at cold temperatures. Well, this vibrating or oscillating matter actually produces light. Not visible light, well, sometimes visible light. So if you're talking about something like a candle flame is going to produce not only heat, it will also produce visible light. But there's an awful lot of things that so a flame, we're talking about something that's very hot and so they're vibrating very fast. If you were talking about something that's sort of cold, like an ice cube, you might go, ice cubes don't emit light, but they are still vibrating. I don't care what kind of matter you have, what kind of substance you have, ice or ice cream or stars or the planet Pluto, all of the different molecules in there are oscillating gently back and forth. So if you're talking about something cold like an ice cube, it's not going to produce anything visible, but it will still produce a little bit of light in the heat part of the electromagnetic spectrum, which is the infrared portion of the spectrum. Every color of light is related to energy. And so if you're talking about things that have a long wavelength, low energy, remember the L's go together, long wavelength, low energy. If we're talking about just the visible part of the spectrum, long wavelength, low energy, we're going to find that on the red end of the spectrum. If we are looking at high energy, short wavelengths, we're looking on the blue and violet end of the spectrum. And one of the examples that you may be familiar with is laser pointers. If you look at cheap little lasers, I don't know about you, but I have a cat and I have a cheap laser that cost under $5 that I bought at the local store, and I use it to entertain the cat. We run the laser all over the living room. She chases it and we laugh at her. It's a good time. But these are cheap, low energy lasers. They're not going to cut through very much. If you get a high intensity laser, you can get green lasers. Now these are higher energy, more energy. And sometimes if you want a laser to penetrate through fog, or you want lasers that are actually can travel further, you're going to use a different color laser, one that is more energetic. Blue lasers, you're not going to find a lot of blue lasers cheaply and easily accessible. Why? They are very, very high energy. Blue lasers are used much more by situations where they want to cut something, or they are used for a situation where people want to weld things. The point I want you to get is the color of visible light is related to energy. Red light tends to be low energy. Blue light tends to be high energy, and there is a relationship to the different electromagnetic waves. Now, every object vibrates, and because of this vibration, it produces electromagnetic waves. Well, it produces not just one kind of electromagnetic waves, it produces many different electromagnetic waves. And if you take a picture of all of the wavelengths produced by an object, it is going to produce what is called a black body diagram. Now, a black body diagram, why in the world is it called a black body diagram? Because 150 years ago, when people first started studying these, they were talking about hot objects that did not emit light. So they're talking about things that were black, but very, very hot. And then the term stuck for black body diagram. This is a picture of a black body diagram. Sometimes it is also referred to as the spectral curve for a black body radiator. Here's what I want you to understand. Every object produces a unique one of these curves. Right? Some of the light emitted by an object might be in here, in the visible part of the spectrum. Some of the wavelengths emitted by an object might be here in the ultraviolet portion of the spectrum. The same object might produce some heat, which is in this portion of the spectrum, and it might produce some radio waves, which is in the long part of the electromagnetic spectrum. Every object, you, me, tadpoles, and your cup of coffee, each has a unique black body curve. Now, there is a peak to each one of these black body curves, and where that curve peaks, when a scientist takes a picture of an object, specifically a star, and looks at where that curve peaks, that corresponds to the color that we see. So we are going to see that color because that is the dominant color for that object. So if we look at a blue star, it's going to emit all of these different electromagnetic waves, and the peak is going to be in the blue region. Hence, it's going to appear blue to our eye. If you talk about a slightly cooler star, lower in energy, like our own sun, its peak of its curve is going to be a little bit lower, and it's going to have a different temperature. Red stars are cooler still, and they are going to have a different peak to their black body curves. Now, when you look at the black body curve of stars, high energy stars tend to peak towards the blue end of the spectrum. Cooler stars, low energy stars, their peak is shifted to the red end of the spectrum. So we get our blue stars over here, and we have our white star in the middle, and we have our red stars that are going to peak down here someplace. Now notice it said white star. This is very much like our sun. Again, it has a whole unique black body curve, but the peak is in that yellowish region, and it gives all of the colors of the rainbow. That's our star. That's our sun. We began this section asking the question, how do you take the temperature of stars that are light years away? Well, the bottom line is we look at color. The overall color of the star is directly related to the temperature of the star because of these black body diagrams and where they peak. So here's how this works. If you have a hot blue star, it's going to have a peak in the blue part of the spectrum, and it's going to appear blue. If you have a cool star, it is going to have its peak in the red part of the spectrum, and it's going to appear red. So low temperature stars tend to be red, and high temperature stars tend to be more towards the blue color end of the spectrum. This is so confusing because this is opposite, absolutely opposite how water faucets work. In a water faucet, blue is cool and red is hot. Well, stars do not work like water faucets. So cool is red and hot is blue, and you definitely need to know that. So here's some examples. This happens to be a red giant star, and this red giant star, red giants are in the end stages of life of a star, and they tend to be red. They're big, cold stars. Medium stars like our sun are in the yellow and white area. And if you get hot stars, well, they're going to look blue. This is the star cluster known as the Pleiades in the constellation Taurus. The Pleiades is the seven sisters, and the Pleiades are blue stars. And what does that tell us? They are hot, hot, hot stars. Okay, let's see if you understand what we've been talking about. Which constellation is this? Orion. Yes, it is Orion. We use Orion a lot because it's a pretty cool constellation. Now, of the stars that is pictured, which one is the hottest? Which one do you suspect is the hottest? Probably it's going to be Rigel or possibly Bellatrix. These, Mintaka, Al-Nalam, and Al-Natak, those are all three big bright blue stars. And Safe, what about Safe? Is Safe as hot? No, Safe is whiter. It's a little bit cooler than these bright blue stars like Rigel and Bellatrix. Okay, which star is the coolest in the Orion constellation? Betelgeuse. Betelgeuse is a big red star, reddish orange, and that is the star Betelgeuse. Now you might see this right here and go, that's kind of pinky red. That is actually a nebula. Nebulae are clusters of gas and birthplaces of stars, but that is not a star. That is actually a nebula. We'll talk more about those later. So let's review everything we just went through. All matter vibrates. That vibrating matter produces a variety of light waves and gives us what's called a black body curve. Where that curve peaks is related to the temperature of the object. So when we see the temperature, the color that is dominant, we know the temperature of the star. Pretty simple in concept, difficult, of course, in scientific methodology. Before we leave this concept of temperature and color, I want to look at light bulbs, because in the modern age, when you and I are buying LED light bulbs, you may never have noticed this, but on the package for a light bulb, there is always going to be a temperature. And it's given in degrees Kelvin. Kelvin is the same size degree as degrees Celsius, but Kelvin goes down to absolute zero. So this LED light bulb that I have pictured here has right on the box 6,000 Kelvin. That tells you where the black body curve peaks for that particular light bulb at 6,000 Kelvin. This light bulb says on it, and it's hard to see, but right there, 5,000 Kelvin. That's where the curve peaks for this light bulb. And this light bulb peaks at, where is it? It's someplace right there, 2,700 Kelvin. 2,700 Kelvin is much cooler. Okay, cooler, hotter. Which one of these light bulbs is going to give you light that is more blue? Which one of the bulbs is going to give you light that is more blue? The hotter bulb or the cooler bulb? That's right. This one is the hotter bulb. It's going to give you the bluer light. This is the cooler light bulb, and it is going to give you warmer light with more red tones in it. This one, notice it says right next to the light bulb, daylight. So it's going to be in the middle, not bright blue, not red light. This one aims for being more balanced across the spectrum. Here's one more picture of a scene photographed using different temperature light bulbs. And remember, they don't get this hot because this is nutty crazy hot, but that is the peak of that black body curve. If you're talking about cool blue, I said that so wrong. If you're talking about blue light is going to have higher Kelvin temperatures. Red light, warmer colors, are going to have lower Kelvin temperatures. So next time you buy a light bulb, take a look at it. It's pretty nifty. All right, we will stop this one, and next time we're going to talk about chemical composition. See you then.